You don't know what's on my mind. You don't know what's on my mind. So I'm gonna give you what you came here for.
Hi and welcome back. My name is Timothy Werder and welcome to the new channel, Let's Do It on a Pie. If you've been following me along this summer on my other channel, linked down below, I've been working on an autonomous vehicle project. If you haven't, let me introduce you to Mega Gearus. Mega Gearus is a four-wheel drive, DC motor-driven vehicle that uses 4 types of sensors to help it navigate the world and pick up its designated targets. These guys. Before I get into the sensors, I want to talk to you about the mission Mega Gearus was tasked with, put on by the University of Maryland at College Park. In a 12 by 12 foot area, multiple colored blocks, some objective colored, some not, were scattered about. In the base corner, the robot starts by facing the positive x-axis. In the north corner, there's a 2 foot by 2 foot drop-off zone where the robot will need to drop off the designated targets and avoid picking up the wrong colored ones. As you might have noticed, none of the 4 corners of this area have any distinct markings aside from some tape on the ground. This means that if our robot needs to know its orientation and position in order to navigate there. So how does Mega Gearus work? First, the robot runs through this mini computer known as a Raspberry Pi. I'm using the 3 Plus. This computer sends out signals to motor controllers, lights, claws, and takes in information from the various other sensors on it, all of which are run via a Python script that follows a simple pattern of analysis, decision, control, and performance. Analysis tells the robot all of the prevalent information and what state it's in, like if there's a green block it would like to pick up. Decision lets the robot choose what's going to do. Is it holding a block? Then it needs to drop it off and calculate that trajectory. Control helps the robot keep in line with what it's trying to do, like lining up the camera and claw with a block it wants to pick up, or drive in a straight line when one of the motors is lagging behind. And performance, where the robot must perform the chosen action based on the analysis, decision, and feedback in a state where it's not receiving feedback. This is to ensure that loop time and sensor accuracy is maintained before the next action. Next up are the sensors. The robot uses a number of ultrasonic sensors to determine the distances. I have 3. The lowest will verify that an object is in range, and the 2 up top will prevent the robot from hitting the walls, as well as allow me to even out my robot when I do get too close. On the claw mechanism, you'll notice there's this switch, which will be triggered to confirm that we've grabbed an object, and that it hasn't slipped out while we go drop it off. Next, you see right in the middle is a Pi camera. I've used color masking to locate objectives, find their centers and the contours to give me an approximate bearing and proximity to the vehicle as we attempt to locate the blocks. Finally, we can look at the undercarriage. You'll notice 2 of these wheels, there are these little discs. These are encoder discs that help us track the position and orientation of the robot. Using these sensors should allow the robot to find objectives and know its bearings. If you've ever worked with robots though, you'll know not everything works out as well as it does on paper. Particularly, my robot struggled with issues with the encoders, whether that's slip, miscounts in the loop, overcounting due to failure to overcome frictional forces, or undercounting due to robotic momentum. Now, before I go into how I solved this issue, let me take you on a bit of the journey in the build of Mega Gearus. So how did I solve this issue? Well, I slammed my robot. No, I didn't take my robot and throw it on the ground. SLAM, or simultaneous localization and mapping, is a method that roboticists and engineers use to help a robot figure out its position based on some known ambiguous data or landmarks, like its angle of approach and other sensors like the ultrasonic sensors. I figured, even though I couldn't 100% trust my encoders, I could get a reasonable angle from them. Knowing the angle, I used the ultrasonic sensors to give me a distance. I could line up my robot and reevaluate my position. But how well did this turn out? Well, let's see. Alright, today we are at the Grand Challenge. We're showing off our robots. We got mega gears down here. As you can see, we've got our starter zone, and then out and about all in this area, we've got different blocks that we're picking up, and then over here in the other corner, we gotta drop them off. So hopefully, if everything goes as planned, which if we're not obeying Murphy's Law, then it should. But we'll have to see and check out these results. August 13th was the day of the Grand Challenge, and it was quite a challenge. Even though my robot wasn't perfect, it still performed reasonably well, given that I only used the sensors provided in the project, and what I had on hand. This coupled with the issues of uncertainty with the encoders. I certainly had fun building and testing this project. I've got a bunch of different projects going on, and if you'd like to learn more about robots or follow along, hit that like and subscribe button below. And thanks for watching.